Hi everyone, uh, I'm Rohit Kumar Singh and I'm the teaching assistant for this course, Nuclear and Particle Physics. And this is the 8th live session. This course. So today I'm going to discuss some concept of relativistic, uh, I mean basically the relativistic approach to uh, understanding, how a free particle behaves. Uh, so this is something we call Klein-Gordon equation. And but first we will learn some notation of two of four vectors and how the four vectors transforms. So let's start. So we have the Schrodinger equation. Uh, from quantum mechanics. So Schrodinger equation in 3 dimension. It's written like this, right? Now here you can see that uh, the time derivative is of first order, but the space derivative is of the second order. So space time is not on equal footing here. So although this equation is uh, fine for non-relativistic case, but when we go to uh, when we go on to describe particles in relativity, we need something else, because we know that uh, in relativity we have different frames, and an equation should be covariant between different frames. And since these this equation has different order of space and time derivatives, so it cannot be covariant in different Lorentz frames. Okay. So this is why we need different equation in the relativistic case. Now, but first we need to know some notations. Uh, so let's draw a comparison between what we already know. So in non-relativistic case we have Euclidean space everywhere, which is the 3-dimensional space, and here a vector can be represented as three-dimensional vector having component x1, x2, x3, right? And a dot product between two vectors is simply just, you know, sum of the components, sum of the multiplication of the corresponding components, and this is denoted as by this, right? So here delta ij is called Kronecker delta, and it is a simple matrix having all the I mean the component on the diagonal as 1 and all other as 0. So like this, and then okay, and the convention is that it's called Einstein convention. So the repeated indices should be multiplied. So here this means that so pi this just means that a1 b1 plus a2 b2 plus a3 b3. Okay, now this is fine for the three-dimensional case. No, but when we discuss yeah uh, yeah sorry now when we discuss the space time together, we have to consider a different space called Minkowski space, which is a four-dimensional space, and here a distance vector x is given by this. So its first component is time, and then the other three components are just the spatial vector x. Okay, so and it is denoted by like x mu instead of simply x. And so there are two distinct possible ways. So first is this, and then the other one is having a lower indices, and this comes with a negative sign for the spatial part. Okay, but these two have the same information. There's just the sign change. So, but both transform in different ways. So, we know that in relativity we have that we, between two Lorentz frames we can transform using Lorentz transformation, right? Uh, so these two vectors transform in different ways under Lorentz transformation. So the first one is called contravariant. So this is, we will see in a while how how do they transform, and this one is called covariant. Okay, and they are related to each other by this relation. Uh, or So going from covariant to contravariant, we do this, and going from contravariant to covariant, we do this. Now, what is this eta mu nu? So, this eta mu nu is uh, called metric tensor, and it has, so it is a 4 by 4 matrix, having the diagonal elements as non-zero, others as 0. And you see that in contrast to the Kronecker delta that we have in Euclidean space, here here in Minkowski space, uh, the signatures are different for time and space. So when you multiply x mu by eta mu nu, uh, the time component will remain positive, but a special component will get a negative value from this metric. So what happens now is, if you try to find a dot product of two vectors here, so like a dot b, where these are four vectors a mu b mu, and as we mentioned, the repeated indices are summed over. Okay, and this is same as a mu b mu. So as long as they are, one is up, one is upper index, other one is lower, it doesn't matter how, in which order you write them. Okay, and as we mentioned here, so we can write, we can go from the covariant to contravariant using this relation. So this we can write as uh, okay, we have to yeah, let's change the b mu to let's lower this index, so keeping the a as same, and then we can use the eta mu mu, and we can write the d mu where the new index is in lower part. Okay, So let's take this out. We have this, and now we can you can see that suppose A and B have components like, so suppose A is A0, so A mu is yeah, A0 and A vector, and B mu is B0 B. Then this will give you what? So this will give you from the using this expression for the metric tensor, you will get, sorry, you will get this value. So what we say is this dot product is invariant under Lorentz transformation. Okay. So even if you change to a different frame of reference, this dot product would remain the same. Okay. So this is why we have a metric like this, so as to ensure that a dot product between two vectors remain invariant under Lorentz transformation. Okay. Now, so this is all for vectors. Now, we can also have different expression for derivatives. So, in four-dimensional Minkowski space, uh, del mu represents this quantity, which is a four vector having first the time derivative and then the spatial derivative. Okay, and this is called covariant, as we have the covariant vectors. So this is called cogradient, and then we have the contragradient, which is just the opposite. And this has a negative sign for the spatial coordinate. Okay. Now we can define here something called uh, D'Alembert. So what it is? So it is just the dot product of these four vectors of derivatives, and you get this quantity. So this is our D'Alembert. and you know that this is called Laplacian, right? The spatial derivative delta. Now similarly, we can also define for momentum. So for momentum p mu, which is defined as this. Okay, so first component is just the energy, and the third component, the all other three components are the three momenta, px, py, and pz. Okay, so this is the contravariant, and the covariant one we can write with a negative sign. And here we have assumed that the speed of light c is equal to 1. Okay, so now what, so why we have defined like this? So let's take the dot product of p mu. So basically p square. So if you take the dot product of these two vectors, you will get e square minus t square, right? Which is just the, sorry, yeah, and then so you can write e square is equal to p square plus 3 vector p square, right? And we know that in relativity e square minus p square is equal to m square, right? So this means that this 4 vector product p square is just m square, mass square. Okay, again we have assumed that c is equal to 1. So this is the Einstein relation for a free particle, right? So let me just write it. Okay. Now let's come back to the quantum mechanics. So in quantum mechanics, uh, so our four momentum will be just this thing, right? Or you can write it like this. Okay. Similarly, the covariant one, you can write it like this. Okay. So using these, you can I mean, you can write the p square again for a quantum mechanical particle, right? So it will be just IH square del by del t square minus delta square. Okay, but this is not what we are interested in right now. I mean, obviously this expression will come into play. We will see how. And so it is simply IH square, and this is our D'Alembert that we defined. Or you can write it like this. Okay. Now, in non-relativistic case, what we have for the energy, so the total energy is given as the kinetic energy plus potential energy, right? Now I have written the kinetic energy in terms of momentum, uh, so 3 momentum, because when we go to quantum mechanical picture, what we do is we promote the dynamical variables of the observables to Hermitian operator, right? And so the momentum, we know the operator form of momentum, so this we can write, and we also know the operator form of energy. So this is basically what gives you the Schrodinger equation for non-relativity. The time-dependent Schrodinger equation. Okay. Now, in the relativistic case, what do we have for the energy? So here the energy is equal to the 3 momentum square plus mass square for a free particle. Let's not talk about any potential. We will see what happens when there is a potential applied. Okay, so for a free particle, this is what we have. Okay, and we just saw that this we can write. So we saw that the dot product of four momentum is just the mass square, right? So we can write it like this. And then suppose we have a wave function, or in this, in relativity we have a wave function phi x. So then like we did in the non-relativistic case, we promote the momentum to a operator, to a Hermitian operator, and write the equation like this. So now the momentum here is, we are talking in terms of quantum mechanics, so the 4 momenta is a 4 momentum Hermitian operator. Okay, and which we just found out that it's equal to the minus h bar square D'Alembert, right? So we can write our equation like this, and here we have assumed that h cut is Planck constant is 1. Okay, so this is done for the convenience. We can put back it whenever we like, uh, but to keep everything clean, we assume this. Okay, so this equation is what we call the Klein-Gordon equation. Okay, and this equation, and we just saw that this D'Alembert is what this is just the dot product of the four derivative, right? So this, and mass m square is dot product of four momentum, right? So this whole equation is invariant under Lorentz transformation. So it is a scalar. You can say it is a scalar of Minkowski space. Okay. And now how to find the solution for this equation? So can you guess what would be the solution? Is anyone connected? Chendur, can you guess the solution of this equation? What kind of solution you will have? Hello, can you hear me? Hello, are you speaking? I cannot hear you. Okay. So we can see that this is nothing but a wave equation. If m is equal to 0, then this is just the wave equation of for a plane wave, you can say. And because if m is equal to 0, then we have only this, and this is nothing but this thing, right? And this is the wave equation that we know from electromagnetic theory. So one guess would be that the solution for this Klein-Gordon equation can be plane waves, okay, and which we know are the characteristics of free particle. So solutions like this, okay, where k and x are four vectors, and so this we can write, and in terms of the three vectors we can expand it like this, where k0 is the first component of the 4 vector, and the k vector is the other 3 component. Okay, now we can say that this k mu are eigenfunctions of this energy momentum operator. So how do we know that? So so to check that, we can just apply the energy momentum operator. So this is the four momentum operator on these plane wave solutions. Uh, and what we get is, so we have to just differentiate in terms of x with respect to x, and this will give us k mu odd, because it's an exponential function, so this is what we expect, right? So indeed, the k mu are the eigenfunctions of this energy momentum operator. Okay. Now, so we say that plane waves given by this equation define a solution for Klein-Gordon equation. So, but it has a condition. So, provided that k square m square is equal to 0, right? Or you can write it like this. And so k0 is equal to just plus minus k square plus m square. And this k0 is what we call our energy, E. So now you see that this Klein-Gordon equation, solving the Klein-Gordon equation gives us a wave function with negative energies, right? So both positive and negative energy states are possible, and this is very peculiar, right? So what does it mean to have a particle of negative energy? It has no meaning, right? In classical sense, at least. But later you will see that it has a very profound implication, and this problem was solved by Dirac by introducing the Dirac equation. So this, I think, will be discussed in the next week lectures. But so yeah, right now we have this Klein-Gordon equation, and it gives us negative energy states. Okay, which is a little peculiar, but still we are able to write some solution for a free particle moving with relativistic speed. Okay, now so again I'm writing the Klein-Gordon equation here, and we can write a complex conjugate of this equation. Okay, so this is the uh, kg, and this is complex conjugate. Okay, now if you multiply this equation by the complex conjugate of phi, and this by phi, and subtract both, you will get this. Sorry. Yeah, right. And this you can write as okay. Now how do we go from here to here? So it has a trick to it. So I will show this when we will solve a problem later. Okay, so how I obtained this thing from here. Okay, but for now just assume that okay, this is possible, and we can expand it into in terms of time and spatial components, and we will get this thing. So for time, uh, this is what we get, and for the spatial coordinate, we have the gradient. Okay. Now, if we define a kind of probability current, so in quantum mechanics we have a probability current uh, for wave functions, right? So similarly, in the relativistic case also we can define probability current, but it will be a 4 vector, and having a time component j0 and spatial coordinate. So we can write the time component as rho, and where j will be uh, this quantity. So we are defining it so that we will get a nice relation between rho and j. So let's so wait for a minute, and the rho is defined as this. Okay, so now if you see from here, this is nothing but del rho by del t plus gradient of j is equal to 0, right? Or you can write it like this in terms of 4 vector. Okay, so this is called continuity equation. Okay, uh, so it basically says that the 4 vector gradient of 4 vector derivative of the probability current is 0. Okay, now uh, one interesting thing we can see from here is for phi x. So for plane wave solution of the Klein-Gordon equation, rho will be simply this, right? Which is plus minus. Now you see that because we had positive and negative energy states, so the I mean the probability density will also have negative uh, value, right? But this cannot be possible. So rho, I mean probability cannot be negative, right? It doesn't make any sense. So this makes the Klein-Gordon theory inconsistent. Okay, uh, and so this is why we abandon it in terms of quantum mechanics. But yeah, in classical field theory, the Klein-Gordon equation is still studied, and but in quantum mechanics, this Klein-Gordon theory leads us nowhere, because we get negative probability density at the end, which is just not possible. Okay? And so we need another kind of equation of motion for relativistic particle, uh, which will give us probability densities not negative, and that's where the Dirac equation comes. Okay? So we will see that later. Okay, so yeah, this is all I wanted to recap, and now we can uh, go on to solve some simple problems. Okay, so anyone has any doubt here? Okay, if not, then let's solve this simple question. Okay, so here 4 vector is given like this. So these are just mathematical question, nothing to do with physics, just to get you acquainted with the 4 vector notation. Okay, so two 4 vectors are given like this, and we have to find the scalar product. Now you know that uh, to to find this scalar product, we can use the metric tensor uh, for the four dimensional space, right? So we can write like this, right? Oh, sorry. And so, and we know that this metric what does is, so it has positive time signature and negative space signatures. So in the end, what you will get is, uh, so let me write it in terms of four vectors. So a mu, you know, is just x plus y minus y 3z square, and this will give you 1 minus 3z plus y and 0, and multiplying these two, and so you know that the repeated indices are summed over, so 5 plus 2x plus y into minus 3z plus minus y into y will be y square minus y square, and this will be 0. So you have 5 and these all okay, so let me calculate it. So this will be minus 6xz minus 3yz minus y square. Now x, y and z are given as 1, so we can put this value. So minus 6 minus 3, and this is minus 1. So minus 6 minus 3 is minus 9, and minus 1 minus 10 plus 5. So the answer will be minus 5. Okay. So we just what we did is, so both the four vector were given in the contravariate form. We converted one of them because to get this scalar product we have to convert one of them into covariant, and we did that using a metric tensor. Okay. So is it okay? Okay, now we can go to the next problem. Now again, for the four vector given in previous problem, we have to find the gradient delta mu A. Now we know that this is same as, so, and A mu is given here 5 plus 5, oh sorry, minus 5 and 3z square. Okay. Now this we know that is so we just saw that this is the this is the co-gradient, right? And this is written as, sorry, this can be represented as this. Okay. So since none of these components are function of time, so this one operated on the whole vector gives you 0. So what basically remains is applying the spatial part on this vector. So on the first component, since it's constant, it will give 0. On the second one, it will give you 2 plus 1, and then minus 1 plus 6 z, right? So at the end you have 2 plus 6 z. Right? This one is also very simple. Okay, then let's go to the next problem. Here the 4 momentum of a free particle is given. So first component is energy, we know this is 50 MeV, and the 3 momentum is given like this. So Px, Py is 0 and Pz is given as 40 MeV per C. Okay, and we have to find the mass of the particle. So we know that mass of the particle is just the scalar product of the 4 momentum, right? And so to find the 4 momentum, so suppose this is the covariant one, so 50, 0, 0, minus 40, and the contravariant one, the time signature is same, but the spatial part will be negative, so this, and then we will just sum the products. So 2500 plus minus 1600, okay, which is this is the mass square actually, and we will get 800, no sorry, 900, and so mass will be just square root of this, which is 30. Okay, again a very simple problem. Okay, so let's move to the next problem. Now here one function is given, uh, having only the spatial coordinates, and we have to find the 4 vector gradient. So again this is just the covariant, I mean the cogradient uh, given by this, and applying the time derivative will give you 0, so just the spatial derivative remains. So applying this spatial derivative on 3x square plus 2y gives you 6x plus 2, right? Sorry, we have to do it component wise. So it means we have del x, del y, and del z, and here we have 3x square plus 2y. So first applying del x, it will be 6x. Applying del y, you will get 2, and del y del z will be 0. Okay, so finally you will have the derivative as, so time component is 0, and then 6x, 2, and 0. Okay, so this is the correct option. So this is how you can take the four vector gradient of any function. Now we have to find the D'Alembert of a function, right? So again we can do it in the same way. So let's first take the derivative. So again because the time because this function is independent of time, so first component will be anyway 0, and we have del x, del y, del z, uh, and since this is the contra gradient, so everything will have a negative sign. Okay, applied on this. So what we get uh, so minus del x minus del by del x on x square, it will give you 2x plus 2y, then minus del by del y, it will give you 2x, and this is 0. Now uh, this we can write component wise as this, applied on 2x plus 2y 2x 0. Okay, now let's see. So del by del x on this, we get minus 2 del by del y, uh, oh wait something is missing. Yeah, yeah, okay. So this will be multiplied with this will go with this, and this will this. Okay, so let's write another step, and then it will be clear. So it will be like this. Okay, so finally what you get, so uh, minus 2 and plus 0 plus 0, right? Because this is 0 and this is 0, and del y del x up to y is also 0, so finally you get minus 2 as answer. Okay, so any question here? Okay, if not, then let's go to the next problem. So as I mentioned here, so when I was discussing the Klein-Gordon equation, I mean when I was discussing how we can go from this step to this step, I told that we will see that in a problem. So this is this problem. Okay, now here we have given the probability current, and we have to find we have to see if this continuity equation satisfies or not. Okay, so what so let's just take the derivative for derivative of the probability current, and sorry, it doesn't matter, but for consistency, let's choose this convention. And I minus 2 del mu of phi, del mu of phi star, and then phi will be common, and then del mu of phi star minus del mu of phi star uh, del mu of phi, and then phi star del okay. Now you will see that this and this thing is the same, right? Because because we know that the sum, the indices are summed over, like, so what I am saying is del mu phi, del mu phi star is same as writing del mu phi, del mu phi star, right? This is the same thing. So this one and this one cancels, okay? And what you get is minus phi star del mu phi, and this is nothing but the expression that we had earlier, right? And we know how to obtain this expression. So like we did here, we multiply this with phi star and the conjugate one with phi, and then we subtract and we get this equation, right? And so we are going in the reverse manner. So earlier we went from here to here, now we are going from here to here, okay? And this is 0 because we know from the Klein-Gordon equation. So you can write this 0. So indeed the continuity equation holds, okay, for this probability current. Now, as I mentioned that so when we were discussing the the relativistic case, we assumed the free particle to simplify things. Now here we are introducing potential, okay, this 4 potential, and then the phi is a solution of the Klein-Gordon equation in external electromagnetic potential, mu. So you know that a mu, sorry, yeah. So we know that a mu is written like this, where the first component is the scalar potential uh, for electric field, and the other three components are magnetic potential, which gives rise to the magnetic field. So basically magnetic field is del cross A, and electric field is gradient of scalar potential, and if it is time dependent, then del A by del T comes. Okay, so now with this potential, uh, what will happen to the Klein Gordon equation? Okay, so that we have to see, but first uh, let's just apply the del mu on this probability current. Okay, and this will give uh, and so I am first applying the derivative on this first term. Okay, and I am writing directly the scalar product of derivatives as D'Alembert box operator. Then for the second one we have this minus phi star box phi, and for this term you will get this. Okay, so let's call it equation 1. Now uh, now how to modify the Klein Gordon equation for electromagnetic potential A mu? So this is done by transforming the derivative like this for the Klein Gordon equation. Okay, and Q is the charge of the particle in the electromagnetic field, and so your Klein Gordon equation becomes this, right? Operated on phi. Okay, so this is the modified Klein Gordon equation. Uh, for a particle, for a spinless particle inside a electromagnetic field. Okay, and we can simplify this equation, so we can just multiply these together, and we can write it like this. So box, because del mu scalar product, it will be just the box operator plus iq. So iq I'm taking common, and del mu of a mu plus 2a mu del mu plus iq a mu plus m square phi of x. This thing is okay, and again we can write the complex conjugate equation. So complex conjugate means I becomes minus I and everything remains the same. Sorry, this one should be minus I. Wait. Oh no, this one is plus I, this one is minus I. And the phi star is the complex conjugate function of phi. And again we do the same thing as we did before. We multiply it with phi and this one with phi star, and we subtract the both. So subtracting, what we get is this thing. Okay, now let's call it equation 2. Now from equation 1 and equation 2, if you look at this carefully, what you see is so since this is 0, you will find here that first of all again we have this and this cancel out, this and this is here, right, and this whole thing is also here, you see. So that means this whole equation is 0, and so we can write del mu j mu is equal to 0 from 1 and 2. So again we see that the continuity equation holds when we have the probability current defined like this for a particle in an electromagnetic field. Okay, so this was the last problem for today. Do you have any question or anything you want to ask? Okay, if not, then let's end today's session. See you next Saturday. Bye.